In this video, we're going to go over the considerations you should take when designing for a 3D print, and in this case would be the orientation of your print, because there are different strength properties and depending on how you print your part, and it's a good idea to understand the weaknesses and the benefits that these orientations have, so you can design accordingly and print accordingly. So a brief overview of what we did for NCUR research this year was we took tensile samples, these dog bones, we printed them out of ABS, 100% infill, and we printed them in 3 different orientations. This orientation, this actually horizontal piece here, was printed like this, my hand being the bed of the printer. And it started down here, and it came across over and over and over again. And actually this is exactly the same as this piece here, as you'll see in more videos. And we had to put supports there for it to print correctly. And that was the first orientation. Second orientation was what we called a flat piece, and it was printed like that if my hand were the bed. And actually it's kind of neat with this piece, you can see more into what the algorithm for the slicer tells the printer how to print the part. And you can see here that there are shell layers. You can actually define how many shell layers you have, and there are 3 shell layers. It outlines the part, and then inside is an algorithm to fill the part, and this was rectilinear, and this is 100% infill as well, but it will still do that pattern to fill in the body basically of your part. So that one's kind of interesting in that respect. And then our last orientation was vertical. This one was printed like so, with this end on the printer bed, and this one was, as you can see, every layer like that. You can kind of see the texture. And we pulled these apart, found out how much force it took to break them, took the cross-sectional areas and averaged what their strengths were. And for reference, ABS is rated about 7,000 psi according to Engineering Toolbox. That's assuming you have a solid block of ABS. Once it's printed, your strengths are lower. For this piece, this was one of the strongest, most consistent pieces, because you can see the grain is, or you can call it a grain, is in that direction, and it resisted being pulled apart the most. And this one actually had about the same average strength, about 6,000 psi is what these ended up being. This one was less consistent, it had a larger standard deviation, but it still was about the same average strength. So those 2 orientations are about the same. This one was very inconsistent, and the average was only 2,000 psi. So this layer-to-layer bond, which is essentially what was resisting that load, is not that strong, and it's not that reliable. Because basically the way the printer prints, it starts from the bottom layer and just goes on top and lays another layer on top of it. It doesn't squeeze them together, it just kind of lays it on top. And we actually did some further testing where we smoothed them. So actually this piece, this piece here, you can kind of see there's kind of a shiny part. That shiny part, literally what we did was just took some acetone vapor we boiled acetone and dipped it in there for a little bit and brought it back out. And the little bit of acetone vapor actually was able to smooth it. And this didn't increase the strength, but it increased the reliability. It reduced the standard deviation. So it helps the layer-to-layer bonds, as we decided that this one's actually smooth too. So it showed the most change in the vertical samples when we actually smoothed them. So that will help, but the best idea is just to assume that you're going to have a 2,000 psi orientation. No matter what part you print, every part's going to have that weakness. So this part here, if you pull this apart like this, you're going to have, it's about 2,000 psi, etc. So where this comes into play when you're printing something like a shaft, this is actually an example from one of the projects we had this quarter. They wanted to print an auger, and I printed it one way and Frank printed it another way. So Frank printed his like this. This is the bed, and that's the way he printed it. And I printed mine like this. And I was going for the form, the shape form, but mine's actually not as effective as far as orientation strengths go for resisting bending and torsion. And I'll first start with this one. So that you can see the layers being like that, when you try and torque it, if you're taking DME, this will make more sense. but this resists torsion and it resists bending because of the way it's printed. And I guess it's easier to see how this one fails at that, because the layer-to-layer bonds are the only thing keeping this thing from snapping when I bend it. And when I'm doing torsion, the highest stress for torsion is on the surface there, and it's wanting to move the two layers apart with respect to each other. And that's only 2000 psi that we've tested on that. So while this one does have a better circular form to it, and it might be a higher position, it's not going to be as powerful in being an auger, which in this case it probably didn't matter. But it's very important to consider that when you're trying to design a part to have a load-bearing aspect to it.